We have to do an energy transition just as we did several energy transitions in the past. For instance, the US envoy for climate, I forgot his name right now, John Kerry. You know John Kerry? Have you heard of him? He said recently in a paper in the Financial Times, the energy transition is the new industrial revolution. Which is very strange when you try to understand what he has in mind about the Industrial Revolution. I don't know what he knows about the Industrial Revolution, but it's a very, very strange phrase when you think about it. He's not the only one to do that. I mean, you'll find many other instances. One famous person around the year 2000 was Jeremy Rifkin. Have you heard of Jeremy Rifkin? Perhaps he's forgotten now. He was the big promoter of the hydrogen economy, a phrase which has gained tremendous importance, especially in the EU, about what we should do for hard-to-abate sectors. We have to go hydrogen, right? So the hydrogen economy, thank you very much for your technical help. The hydrogen economy is this idea that there has been several industrial revolutions. The first one was about coal, the second one was about oil, and the third one will be about hydrogen, right? So what's really worrying and what is really strange is that these people, you know, they're taken seriously. Oh no. Okay, sorry, that's... Okay, these people are serious. You know, John Kerry is following the issue of climate change in the 1980s. He's a colleague of Al Gore, perhaps better known. So he should know about that. He should know his history, right? So, I mean, you will tell me that this is just public discourse. This is for, you know, it's an aspirational discourse, right? We have to motivate people to do the energy transition, and to do that, you have to tell them it's, you know, there will be a lot of money to be made. It's just like the Industrial Revolution. What is even more worrying is that if you take the expertise on the topic, and I'm thinking about normally the best expertise, you know, like the last IPCC report, you've got the same strange history. So I guess you know that, but in the IPCC there are several groups. There is group 1, which is about climatology, group 2, which is about the impact of climate change, and group 3 is about mitigation, the solution for climate change. The last report from 2022 is a big PDF file over 2,000 pages. Transition is all over the place. You know, 1,800 occurrences. And it's very high tech. Hydrogen is also extremely present in the report. It's present every other page. On the other hand, sufficiency is only appearing now. It's the first time that you got any substantial treatment of the issue of sufficiency in an IPCC Group 3 report. They have been producing reports for 30 years, right? It's their 6th report. And the issue of degrowth is still virtually absent. I mean, it's only present 26 times in 2,000 pages, and it's mainly in the footnotes, in the references. And I mean, actually, they're completely honest about it. They have received over 3,000 net zero scenarios. You know what these scenarios are? You know, you ask a computer model to simulate how the world economy could reach carbon neutrality between 2050 and 2070. They have received over 3,000 of those scenarios. They are called integrated assessment models. And among all these scenarios, not even one includes any degrowth of any country, even rich country, right? I mean, all these issues, they are for economists. So I'm an historian. I should have said that in the first place. I'm not an economist, and certainly not a climate economist. I'm an historian of technology. But I think it's telling about the status of climate economics in a way. But when they talk about history, there are very strange things. There is a whole part of the second chapter which is about history. It's not a big section, but still it is present. And they try to answer a very, very strange question. This question, can energy transition occur faster than in the past? You know, will we have now a faster energy transition than the previous energy transitions? Or they also say a low carbon energy transition needs to occur faster than previous transitions, which is both true and very strange. It is true that it has to happen faster because there's never been any energy transition at a global level, you know? But it is a very strange phrase. So as you all know, obviously at a global level, which is the one that matters for the climate change, we have not passed the peak of any energy source. There was some hope that 2024 will be the peak coal because of the solar, the expansion of solar energy in China. But unfortunately, in the last World Energy Outlook, which appeared last month, it seemed that the coal peak is postponed to some time probably before 2030, right? Oil and gas are doing fine. We are far from seeing the peak of demand of gas, and oil is probably not close. More surprising, wood energy has grown a lot in recent times. And today, wood energy represents twice nuclear energy in final energy consumption. So, I mean, we have to take into account the very simple fact that we are using old sources of energy, not new sources of energy on a global scale. I mean, this is a very, very obvious point, the one, so it's in French, that the history of tech is different from history of materials. It's a very obvious point, but it's not, I think, clearly, it's not made clearly enough. And this confusion is a source of many, many problems in the scientific literature. We have a tendency to project modes of reasoning which might be valid about technological dynamics, where there are sometimes substitutions, transition from one technology to another. We are projecting that onto the history of energy and materials. And that makes very strange stories. I mean, I will just give you an example. In the history of artificial light, there is an enormous transformation which took place in the interwar period. It is electrification, the electricity. This is really a key technological revolution. There is absolutely no doubt about that. And before that, we were using oil lamps, kerosene lamps, right? Petroleum lamps. This was the low-tech way of producing artificial light quite late in the 20th century, actually, in the rural, in the countryside. Does it mean that we don't use oil to produce light today? Certainly not. Only the headlights of cars consume much more oil, petroleum, than the whole world economy in 1900s, when everyone, or almost everyone, was using petroleum lamps, right? So you got a feeling or an impression of very enormous, tremendous technological change, but the history of material behind these technological changes is much more boring. Everything is growing all the time. It's a very tedious history, right? We are consuming a greater variety of materials, and each material is consumed in greater quantity. There are very few exceptions to this rule. One exception is ship wool, which has decreased since the 1950s by 1/3, and it's because of nylon, which is not a good news for the environment, right? So, I mean, what strikes me is we got so many, literature on innovation as a solution for our environmental problems, innovation as a solution for climate change, blah, blah, blah. But we just have to take into account the very simple fact that, there has been plenty of innovation along the 20th century, and raw materials are never obsolete, right? Okay, so to be fair with the experts of the IPCC report who wrote these very, very strange phrases, it is true that history of energy had a tendency to propose narratives of great transitions. And actually, transition is the main topic of the history of energy. There are several subgenres in this genre of history of energy. The main one, the most influential one, is like the big historical fresco on the energy history of humanity. And very often you've got the same chapters. You've got chapters about the pre-industrial world, which will be dealing about wood and hydraulic energy, chapters on the 19th century and the Industrial Revolution, which will be mainly about coal and the steam engine, and chapter of the 20th century, which will deal with petroleum, right? And that's of course a big problem, because as you all know, coal has expanded a lot since the 1980s, right? Really, the big age of coal starts from the 1980s onward. It has tripled between 1980 and 2010, right? And most of the historians, I'm talking about historians, I guess for economists perhaps it's more obvious, but historians tend to be interested in coal in the 19th century. But 96% of coal was extracted after 1900. So really the history of coal is about the 20th century, not the 19th. Most of coal most of history is about coal in Europe, especially Britain, but 86% of coal was extracted out of Europe. Right? So the history of coal is 20th century Asia, basically. So there is this first subgenre, which is like the great fresco of energy transition. What is even more striking is that people who know that it is not true have this narrative. And I'm thinking about Václav Smil. Have you heard of Václav Smil? He's like one of the best historian of energy. He's very skeptical about our ability to get out of fossil fuels in 3 or 4 decades for, I think, good reasons. But when he writes about history, he keeps talking about energy transitions. You know, there have been several energy transitions. There is a great transition to a fossil fuel economy in the 19th century, blah, 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 right? So there is this genre in history of energy. There is another one, which is equally problematic. It tends to be mono-energetic. So you've got, I got colleagues working on the history of coal, other colleagues working on the history of wood, and other colleagues again working on the history of oil. What I was interested in was the intersection of what is happening at the intersection of all these energies and materials, right? And there's also another genre, but I haven't put the slide here. Perhaps you have heard about it, like more political history of energy. Have you heard of Tim Mitchell? Tim Mitchell's book, Carbon Democracy? Who has heard about Tim Mitchell? Not that many. So perhaps there's no point in showing that this is really a wrong way of approaching history of energy. Perhaps Andreas Malm is better known, Fossil Capital. It is a very transitionist narrative. I mean, if you read Tim Mitchell's book, it's about how the transition from coal to oil altered the power of the proletariat, basically. But it's very transitionist. It even reinforces this very stagist vision of history of energy. If you read Andreas Malm, it's like there is a transition from hydraulic power to steam power. But in fact, hydraulic power is doing fine in the 19th century. It's expanding, actually, in the 19th century. And, you know, industrialists use both. There is no reason why they should neglect hydraulic power. It's a perfectly fine source of mechanical power for the industry, right, in the 19th century. Anyway, so this is a very brief summary of history of energy. There is a very strong stagist narrative in history of energy. The main reason is because it's written in relative terms. What historians are describing when they are talking about transition, they are talking about a change in the share of different energies in the energy mix. This is a famous graph taken from like a reference book, Power to the People. This one on the center, top center. This is a very impressive graph retracing the share of coal in the energy mixes of different countries, European countries. And there seemed to be like very impressive transition from wood and hydraulic to coal, right? Like in Germany, there was almost no coal in 1800, and there is 90% of coal in the energy mix in 1900. So it seems quite normal to talk about a transition here. I mean, this graph relies on several assumptions. First of all, you take every sources of energy and you convert them into energy units, megajoules, British thermal units, etc. The problem with that, especially at this period of time, from the 1900 to the 20th century, there is a big issue about the lack of efficiency of all technologies using coal. They are retracing the share of primary energies, not final energies. This is a key point because it gives the impression of a sudden shift, a sudden transformation as soon as coal entered the scene. But this is plainly wrong, as demonstrated by so many economic historians in the 1970s. You know, coal before 1860 is quite unimportant, in fact. It's not very important. Like steam engine before, like look at this graph. Britain 1800, 80% of the energy comes out of coal. Don't you think it is strange? Do you know how many steam engines there were in Britain in 1800? Around 2,000, right? So the steam engine in 1800, nobody cares. I mean, the steam engine becomes important in the second part, at the end of the 19th century, not even in the middle of the 19th century, right? So, I mean, because they look at primary energies, and steam engines are so inefficient that, of course, you measure what? I mean, right? You got the same thing for many other technologies, like lighting. I was interested in the history of lighting. You can use coal to produce lights. You distillate coal. You create a gas that is a very poor illuminant. It consumes a lot of coal and therefore a lot of primary energy, but it produces so little light, so little useful energy, right? So these graphs are, you know, it's not that they are wrong, it's that they are measuring a very specific thing, which is the share of the share of coal in the primary energy, as primary energy. So this gives the impression of a transition, but in fact, as I said earlier, hydraulic energy is expanding a lot in the 19th century during the so-called Industrial Revolution. In France, it's multiplied by 3, even before hydroelectricity. Wind power expands a lot also in the 19th century, especially in America. You got millions of windmills in the US, which are installed at the end of the 19th century. They are extremely important for the economy because they are pumping water in the Midwest, in the Great Plain of Texas, and like wind energy is really a key energy for the agricultural expansion at the end of the 19th century, which is a very, very important historical phenomenon. Probably more important, in my opinion at least, than the steam engine powering power loom, textile loom in Manchester in 1830. Right? This is a transformation of far greater importance we are talking here. And of course, you got also a stupendous expansion of human muscle energy, because you got more humans, they are better fed, and they're using much more efficient tools, hand tools, but efficient tools. The reduction of friction is not taken into account by classic history of energy, whereas it is extraordinarily important to understand history of energy. And I mean, it's because they are not very impressive technologies. Nobody talk about it. You know, it's not like a railway. It's not like a railway locomotive. It's like very small carts, wheels, rubber wheels, for instance, or ball bearing. These kind of small technologies had a very big importance on the increase of the useful energy produced by the human muscle. And this is a late 19th and many 20th century history. That takes place mainly in the 20th century, this transformation. I mean, just to point out the cliché nature of our understanding of energy and production. The amount of literature on the assembly line, you know, the assembly line, Ford, right? It's so important that there is, I mean, you mentioned the École de la Régulation just a few minutes ago. Like Fordism It's like it seems to represent the 20th century in production. But in fact, I mean, the Fordist model is very marginal in production in the 20th century. I mean, by far the most important technologies are these kind of technologies. In most of the industry, you don't have assembly lines because it's very capital intensive, it's complicated, and you've got these small carts moving around pieces and raw materials, right? Another very important graph which shows another problem with the history of energy. This is taken from Anthony Wrigley, Energy and the Industrial Revolution, a very important book, very famous book. And this graph then has been taken up by most of these books. You know, they use this graph to talk about what has happened during the Industrial Revolution. There is the same problem about primary energy and final energy. This is a primary energy mix. So as soon as you put 1 ton of coal, of course, the energy seems to explode. But in fact, this ton of coal is used in very inefficient technological systems. It's very clear because, I mean, it's kind of obvious because look at that's like the energy consumption of an Italian in 1860 and an energy consumption of a British person at the same period. Do you think it makes sense that there is such a discrepancy? You know, it's very strange, right? Then there is also this graph conveys an impression of transition. There is the expansion of coal, which is predictable. This is the light gray area. And you got the disappearance of fuel wood. This is this one, which decreased and then peters out around 1850. And it is true that in 1850, British people wouldn't normally heat their places with wood. They would use coal. And steel industry in Britain was already entirely converted to coal. Does it mean that wood has disappeared from the energy system of Britain? Yes.
No, because, I mean, it was used in the mines in order
Yeah,
to consolidate
exactly. So coal mines. Coal mines are thousands of kilometers long. They are a huge infrastructure. And they are gobbling up every year at the beginning of the 20th century in Britain, 4.5 million cubic meters of wood. Britain in the 18th century, according to energy historians, consumed 3.6 billion cubic meters of wood, of fuel wood. So just to produce energy, Britain used more wood in the mines, in the form of pit props, than it burnt in the 18th century. Furthermore, pit props, it's like construction timber. So it necessitates far greater area of forest to be grown than fuel wood. So Britain in the early 20th century would consume 4 to 7 times more forest than it did in the 18th century, right? Just to produce its energy, because then there are all the other uses of wood for packaging, for printing press, for printing paper, and so on and so forth, right? So when you've got like Anthony Wrigley talking about the Industrial Revolution as an escape from an organic economy or a transition from an organic economy to a mineral economy, these are very, very strange interpretations, right? The case of Britain is not, I mean, it's kind of singular because it has a very large mining industry and a small forestry industry. But all industrial countries consume more and more pit props in the 19th century and until the 1950s. So this graph, sorry, I should say what it is. This is the consumption of pit props. So it's in cubic meters of wood in different group of countries, Europe, USSR, USA, and China in the 20th century. As you can see, it grows a lot, especially in Russia, in USSR. In 1965, USSR consumed around 25 million cubic meters of pit props. To give you a point of comparison, France at the beginning of the 20th century would produce only 6 million cubic meters of construction timber. So it's really a lot of timber. And it is made possible by the construction of a canal which connects the Volga to the Don, to the Donbass, Volga is a very large river crossing central Russia where there is a lot of forest. And thanks to this canal, the timber from Russia can be sent to the mines of Ukraine. The canal is inaugurated in 1952. It's a great symbol in the Soviet propaganda. It's a great symbol of the friendship between the two people, the Russian people and the Ukrainian people. In 1992, at the collapse of USSR, Ukraine is deprived from this cheap wood, cheap timber, and it is a catastrophe for the mines of Ukraine. So as late as 1992, the mines of the Donbass were still relying on pit props to support the roof of their mines, right? Or at least part of their mines. I mean, I just took this example of coal mines, but all like the big technological system that we tend to reduce to coal actually consumed also a lot of wood. Another example is a railroad. The railroad consumed far more wood than iron, 6 times more, because you had to change the railway ties every 4 or 5 years. And then all the bridges, all this consume an enormous amount of wood. So when you talking about coal, you need to think about the timber that allows you to extract the coal, right? The two are in symbiosis; they are not in competition. The idea that coal enters in competition with wood is really, it's really wrong. It's not like this that we should think upon the relationship between coal and wood. Then the same thing goes, it's probably more obvious, the same thing goes with coal and oil. The idea that there is like a transition from coal to oil in the 20th century is clearly wrong for a very simple reason. Oil is mainly used to power automobiles, and to produce a car in the interwar period, you need 7 tons of coal to make the steel, to produce electricity, to make the glass, the copper, and so on and so forth, right? So a car is just as much a coal technology as an oil technology. Because at that time, 7 tons is more or less the amount of oil that a car would use during its whole lifetime. And today, to produce a car in China, you need 3 tons of coal, for instance. So when you look at a car, you actually look at a big stack of coal. This is, by the way, this is the very famous Ford factory on the Rouge River, and you see a big stack of coal because this is by far the main primary material entering into the construction of a car. And then there is not only the car; it's all the oil infrastructure depends on steel. Steel is everywhere when you think about oil. It's in the tubes that allows you to drill the soil and to get to the oil, in the pipelines, in the reservoirs, in the tankers, in the motors, in the engines. All these are dependent on steel. And steel, I mean, nowadays it's 75%, but in the past it was even higher. 75% of steel right now is made out of coal, made with coal, right? And the rest, it's like secondary steel. You are using old steel and you heat it in an electric arc furnace. But steel is completely dependent on coal. I mean, if you take iron ore and you transform it into steel, most of it is made with coal. And once again, when you look at the figures, I mean, there is a huge symbiotic expansion. Like the oil industry in the US around the year 2000 consumed, there was an oil boom in the US at that point, consumed a certain amount of pipes, tubes, oil tubes, and just the oil tubes, it represented more steel than the consumption of the whole US economy 1 century earlier. You know? So once again, do not think like coal and oil in opposition, but rather in symbiosis. Of course, on certain sectors, there is a competition. Like for transportation, obviously, the diesel engine is so much more practical than the steam engine. In the interwar period, the steam engine are, everybody gets rid of its steam engine and they replace it with diesel engine, which are so much more efficient, right? But nevertheless, all the machines powered with the diesel engine are made out of steel and therefore out of coal. And then when you've got oil, you've got all the other materials that become cheaper, especially coal. Before the dump truck, buying coal, transporting coal was complicated. You would do it with horses, with humans, with shovels, with wheelbarrows, with sacks. A big part of the price of coal was the delivery. And this very unimpressive technology, the dump truck, which seems very basic and not that interesting, actually has an enormous economic importance because it makes the price of coal decrease and the price of actually many ponderous materials decrease. There is also a symbiotic relationship between oil and wood. First of all, without wood, there would have been no oil in the early period of oil, early times of oil. The derricks were made out of wood, and there are big structures, like 30 tons each, and there is over 1 million derrick which are built in the US before 1930. And then the refined products were transported in barrels, wooden barrels. The great age of the wooden barrels is around 1910, 1920. It's when there is the peak of wooden barrel in history. And it's because of oil. And also because of cement, but mainly because of oil. Like the biggest wooden barrel entrepreneur of history is John D. Rockefeller. Like the biggest oil man of history is also the biggest barrel manufacturer in the world. I mean, the pipelines were used very early on in the US, but just to transport crude petroleum, not to transport refined products, which were thought as too dangerous to be transported in bulk. So they would rather use wooden barrels. And once again, there is when I said at the beginning of my talk that wood energy has expanded a lot recently, it is because of oil. There has been a big transformation of the energy system in the poor world. It is the expansion of the charcoal. Charcoal, has expanded a lot with the urbanization in the poor world. It is the first time in history that you've got huge cities, over 10 million inhabitants, using charcoal to cook their food. Lagos, Kinshasa, Dar es Salaam consumed between 2 and 3 million tons of charcoal a year. Paris in 1860 would consume only 100,000 tons of charcoal. Whole French steel industry would consume over 300,000 tons. So actually one city like Lagos or Kinshasa consumes probably more wood than France in the 1900s, right? Or Germany for this point. So, wood energy is certainly not obsolete, certainly not old-fashioned. It has increased with economic development in the poor world. You've got urbanization, you've got electrification, but doesn't make disappear charcoal. Electricity is used, of course, in Kinshasa, Lagos, etc. But they also use charcoal at the same time, right? And it is made possible by the truck. Because for the case of Kinshasa, this charcoal is produced in the Congo basin, so a very large forest, and it's transported over 1,000 kilometers. So you need some modern transportation network to shift all this wood, this charcoal. Charcoal is really an urban technology because it's very inefficient. You use a lot of wood to produce charcoal, but then you can transport it because it's light, and you can put it into sack, which is not the case of green wood, right? And the same expansion of wood energy took place in the rich world as well, which is probably more surprising, because it has not happened in the domestic world, but rather in the production side. The paper industry is a very interesting case to study. The paper industry is a very, very large industrial consumer of energy. It's the fourth consumer of industrial energy in the world. I mean, I don't know if you know the first one. Do you know which industry consumes the most energy right now? I've already talked about it a little bit. Steel. Steel is really the first consumer of energy. In second, you got cement. Third, you got the chemical industry. And fourth, you got the paper industry. And paper industry, starting from the 1960s mainly, started to use the lignin, which is the liquid substance. I mean, they also call it black liquors, a residue of their production of paper. And these black liquors represent an enormous amount of energy. For instance, in Europe, black liquors, you can see it here. You know, wind energy has overpassed recently the black liquors. And solar energy is overpassing right now the black liquors in Europe. So, I mean, black liquors, we're not talking about a small thing. And then there is all the wood pellets, wood electricity, which has grown a lot in Europe. In the US, as you can see, there is the use of wood energy in industry. This is twice as much as hydraulic energy in the US, you know, and its wind power has just overpassed. No, sorry, it's not. It has not overpassed yet. It's still below the use of wood energy in the industry. So it's about the paper industry. It's about all the timber industry, which is a big industry actually. I mean, timber is like the third most used material. You know, oil, coal, oil, and wood. They are and gravel, of course, is above them. Okay. One last example. It's to show, I mean, the fact that energy transition is a very strange notion. It's the case of Drax power plants. I don't know if you've heard of Drax. Drax is an electric power plant in Britain, near Leeds. It was inaugurated in 1974, and at that time, it was supposed to burn local coal. It was privatized around the 1990s. It imported like 9 million tons of coal per year in 1990 from Russia, from South Africa, Australia, from the big coal producers. And then around the year 2000, with a lot of public subsidies, it started to convert to biomass. But biomass is a euphemism for wood pellets, which are produced in the US and in Canada. Each year, Drax burns, well, on the figures I found on their website, 8 million tons of wood pellets. It is much more than what Britain burned in the 18th century. Remember, 3.5 million cubic meters of wood. So 8 million tons of wood pellets is really a lot. It's like at least 4 times more than what Britain burned in the 18th century. So after 2 centuries of energy transitions, we reached this great result that Britain, the leading country in energy transition, the country doing the first energy transition in history, and the first to get out of fossil fuels, or so they say, is burning 4 times more wood than it did in the 18th century. So, I mean, when you take into account the fact that, you know, at the global level, we have passed, I mean, all energies have been growing, that all energies are completely intricated one in each other. Without wood, there would have been no coal, therefore no steam, therefore no steel, therefore no railways, etc., etc. Without coal, there would be no oil infrastructure, no cars, right? So there would be no oil, in fact. I mean, there would be no point of extracting oil in a way. When you take into account the symbiotic nature of energy, it is true that this notion of energy transition, of a shift between energy systems, is very, very strange. So the second part of my presentation is how come this notion has become so central, so obvious, so natural, that everybody starts talking about energy transition. It's a recent phenomenon. For the biggest part of the 20th century, nobody would talk about energy transition. This is a graph a kind of futurology of energy for the US, proposed by a solar engineer in 1972. And as you can notice, I mean, the striking characteristic of this graph is that, according to him, everything will grow in the future. Of course, solar energy would expand. He was a promoter of solar energy, but nuclear power would expand, coal would expand. You know, there is room for everyone. And the future energy is not like a very different present. It's a bigger present, right? So it is the way most of people thought about energy before the 1970s. I mean, one hint of that is the fact that US conservationists would be preoccupied by the reserve of coal, and they would ask questions like, will there be coal in 300 years? You know, nobody's asking this question any longer. I mean, there is a lot of coal. We don't really worry about the exhaustion of coal before the 24th century, right? We have other worries, actually, right? So, I mean, which shows that they didn't imagine like the future of US energy very different from the present they knew. So, almost nobody talked about energy transition except one particular group of scientists, and they are atomic scientists, and also they are neo-Malthusians. Malthus? How do you say Malthus or Malthus? Malthus. Malthus, I guess everybody knows him, you know, like late 18th century, early 19th century economist, but also reverend, who had this theory of demographic growth overpassing the production of food. And neo-Malthusianism is a very powerful cultural phenomenon, an intellectual phenomenon, scientific phenomenon in the US and in Britain in the 20th century. It's really a key intellectual domain where many environmental discourses emerged. I mean, the problem of environments are caused by the growth of population. So the first use of the phrase energy transition, to my knowledge, comes from this person, Harrison Brown. He's a chemist working for the Manhattan Project during the war. And he works in a very particular laboratory, which is the Metallurgical Laboratory of Chicago, where there is, of course, Enrico Fermi, who designed the first atomic pile. And in 1943, there are the first calculations made of a very specific nuclear reactor, a kind of imaginary reactor at that time, which is the breeder reactor, or the fast neutron reactor. In this reactor, you can create so much energy with little uranium that it seems to open like an infinite time horizon for nuclear energy. It's really important for them, because most of them, they feel guilty about Hiroshima and Nagasaki. And they want to demonstrate that what they have done during the war is not just a terrible instrument of death, it's also the key for the survival of humanity. It is with the breeder reactor that you can open like a time horizon of several centuries and even millennia to industrial humanity. Because with the fission reactor, at that time, the reserves of uranium were considered quite small, so fission reactors were not that important. You could not power an industrial civilization for millennia with just fission reactor. You need a breeder reactor. Actually, the phrase energy transition comes from atomic physics. It is the change of state of an electron around its nucleus. So Harrison Brown is really recycling a technical word to talk about the future of energy. And he mixes it with the idea of demographic transition, which is another transition which was famous at that time among neo-Malthusians. And he coined the phrase to talk about the future of energy. Another key character in the story is Marion King Hubbert. I don't know if you've heard of him, Marion King Hubbert. If you've not heard of him, you know about his theory, the peak oil. He's like the big theoretician of the peak oil. But, I mean, So he's a geologist, not an atomic scientist, but in 1955 he is recruited by the Atomic Energy Commission. And of course, this idea of peak oil, peak coal, peak fossil fuel is extremely useful if you want to promote the nuclear industry in the US in the 1960s. And King Herbert writes 3 very important reports or chapters in these reports, which are sent to a US president like Kennedy in 1965. I can't remember exactly the date, but in the mid-1960s. And really, this idea of fossil fuels peak, all fossil fuels, even coal, make a peak when you zoom out on the history of energy and the history of humanity. I mean, this graph, the bottom graph, is quite spectacular. I don't know if you can see it in the back. This is the history of humanity on a 10,000 year time scale. So of course, if you consider the history of humanity over 10,000 years, it is true that all fossil fuels form just a very narrow and frail peak. There is not so much energy in all the reserves of coal and oil and gas. But all fossil fuels make a peak also because you contrast it with the unlimited energy plateau that the breeder reactor allows you to reach, right? So really, this is where energy transition emerged for the first time. This idea that there will be complete shift from one source of energy to another. Yes? Yeah, it's completely stylized. It's like, I mean, the x-axis is energy, an energy unit, whatever. Okay. Here you've got millions of kilowatt. For the case of the US, this is the US. Here you put sorry, this one, yes, of course, it's a thought experiment. Yeah, of course. And look at this is for the case of US and oil, petroleum. For him, the peak would be reached in around the 1970s. And it was true of conventional oil, but certainly not true for the rest of the oil, because he would say, I mean, according to Herbert, there would be no oil or almost no oil left in the US in 2020. And now I think US oil production is probably 50% larger than the 1972 production, right? Anyway, so really energy transition is emerged from this small group of promoters of the breeder reactor. But I want to pinpoint the fact that the energy transition, according to them, like the end of fossil fuels, can you see when it takes place in the future? I don't know if you can see. It's midway between now and 1,000 years. So the end of fossil fuels at a global level, well, they leave it a lot of time, you know. It will take place somewhere in the 24th or 25th century, because they know there is a lot of coal, and they know that atomic energy, you know, before it is used generally in all countries for all technologies, it will take time, right? I haven't put the slide, but I think I might have the time to say that atomic energy has also played a crucial role for the identification of the climate change problem. It's not very well known, but in 1953, there is a report published by the Atomic Energy Commission, and they say there is the problem of fossil fuel exhaustion. It is the first problem, but there is also another problem which might be climate change. And why are they pointing out this problem? There are 3 reasons. First of all, they look at long time forecasting. So they are considering the amount of coal that will be used in the 21st, in the 22nd, or the 23rd century. And there is such an amount of carbon going from the lithosphere to the atmosphere that, of course, this problem of greenhouse effect seems to be, you know, you have to take it into account. The second reason is that atomic scientists were the best equipped people to study climate change after World War II, because they had in their hands a key piece of technology, a key scientific instrument, which is the mass spectrographer. The mass spectrographer allows you to measure the proportion of isotopes, of carbon, of oxygen, So it allows you to study in a novel way the carbon cycle or the paleotemperatures. So really, the new scientific knowledge produced on climate change, which is not an unknown issue before 1950, but a kind of secondary issue, it's studied really in a new way by people like Harrison Brown, actually. In 1953, he set up a research project on that, on climate change. Right? And by the way, Harrison Brown was the mentor of Charles David Killing, who is doing his postdoc at Caltech when Harrison Brown was head of geoscience at Caltech. I don't know if you know Killing, right? Charles David Killing. No? Okay, there is just one thing to remember of this course, of this lecture, it is Killing. The Killing curve. Have you heard of the Killing curve? Yeah? No? Okay. So it starts in 1958. He measures the quantity of CO2 at Mauna Loa in Hawaii, and it makes like this. Okay? And now we are somewhere here, right? So this is really a key proof of the issue of we are really transforming the atmosphere. It shows that the ocean is not going to absorb all the CO2 that we are emitting en masse in the atmosphere, right? And do you know why it fluctuates like this? Yes, I'm sure you know, but seasons, right? Yeah, it's because there is more vegetation on the northern hemisphere. So during the spring, the vegetation captures a little bit of CO2, which is in the atmosphere, and then during autumn, it relâche carbon dioxide, right? So you see all the vegetation, the respiration of the whole vegetation of the world in this curve. Quite a striking curve, I think. Anyway, so he was the one who said to Charles David Killing, this is an interesting topic that you should study. Killing was working on the extraction of plutonium or like chemical stuff for the nuclear industry, and Harrison Brown redirected Charles David Killing on this issue of climate change. Anyway, the idea of energy transition, is marginal. It's not a phrase that you find a lot in the literature before the 1970s. The key phrase in the 1970s is energy crisis. And energy transition starts to be used as a generic term for referring to everything which can solve the energy crisis. Energy crisis is really also a kind of invention of the nuclear industry. The phrase appears in the grey literature of the Atomic Energy Commission at the end of the 1960s. There has been a blackout in New York in 1965, which has shocked the US population. It is caused by bad infrastructure, bad electric infrastructure, and other different causes, which are clearly not a lack of coal. There's plenty of coal in the US, but they start to reinterpret it as the sign of something much deeper, which is the exhaustion of fossil fuel reserves. And for instance, this is an advertisement from General Electric in 1972, showing this piece of coal is going to be soon extinct. And we need, thanks to General Electric, who are inventing its successor, which is the breeder reactor. And then there is this guy called Jimmy Carter, US president. And in 1977, he made a very impressive speech on the television, explaining that in the past, the US had done 2 energy transitions. The first one from wood to coal, the second one from coal to oil. And now, with the oil shocks, the US has to accomplish a 3rd energy transition. And for him, it would be a little bit of solar, but mainly it would be, at the short term, it would be about coal. So energy transition was a way to make coal look futuristic, because Jimmy Carter was planning to double coal production in the US in the next decades, which doesn't look very like futuristic, but if you say we're going to do an energy transition, it looks much, much more impressive. So when Jimmy Carter is talking about the 2 energy transitions in the past, he's commenting on this graph, on very peculiar graph. It is from the US energy plan that he's presenting on television in 1977. And you can see 2 beautiful energy transitions here. And of course, the trick is to put everything in percentage, in relative terms. If you do that and you put fuel wood, then you've got a very nice transition to transition. At the same time, people would represent energy like this, you know, where energy transition is not that obvious. This curve was stolen from this guy, Cesare Malchetti, who is an atomic scientist working at IASA, who is the first to create these like curves where you put everything in relative terms and you can see transition appears. And he does that because he wants to criticize what is being done at IASA. IASA is an institution which is really important nowadays for integrated assessment models, the net zero model that I talked at the beginning. You know, they are really the key institution for doing this. And at IASA, they use computer models to study the behavior of the energy system according to different parameters. And in 1972, they were asked to answer to the Club of Rome report. You know, the Club of Rome about the limits to growth. And they were using the same tools, computer models, to show that, in fact, there was a path to a fossil-free world in 50 years. It was what they were asked for. Find smooth energy transition paths out of fossil fuels in 50 years. It's exactly the same demand that we are now putting to the modelers. And since they are using computers, they can do whatever they want and they find very nice paths out of fossil fuels, right? Their strategy is if oil is getting more expensive, you have to increase coal right now, like in the 1970s, 1980s. And then after 1990, there will be a sudden shift to the breeder reactor because we will have the technology. So that's really what they kind of advocate as a solution to the global energy crisis. And Cesare Malchetti didn't agree with that. He was very pro-nuclear, but didn't believe that it was possible to shift like this from coal to nuclear. And so he started to map the share of each energy on the global level, and he created this extremely also famous graph, which is, I think, a key element in the theory of the energy transition. It allows the evolution of the global energy system. It's in relative terms, of course, it's shares of energy. And I mean, this is the data, and this is what he gets from the equation. He has a kind of logistic diffusion model for energy behind these curves. I mean, what is worrying is that according to him, there will be no coal in the world around like in 2020. Coal would have disappeared, right? And now he's criticized, especially by Václav Smil, saying this is rubbish. Look, coal is very important right now. But what is unfair is that Cesare Malchetti was the most pessimistic forecaster of the time, you know. So the most pessimistic forecaster of the time was actually far too optimistic on our capacity to get out of fossil fuels in due time. So the idea of energy transition really started to become like studied and talked about in the 1970s in the wake of the energy crisis. And it was caught up by the oil industry, who liked it a lot, especially when the climate issues started to emerge. So it is in the US in the late 1970s. The reason for the emergence, the political emergence of climate issue in the US is the coal to fuel proposal. Jimmy Carter was obsessed with the problem of energy crisis and said to solve the energy crisis, for the time being, we have to liquefy coal, to make oil out of coal, right? Coal to fuel, synthetic oil. It's very common in South Africa, and it's also used quite a lot in China. So it's an extraordinarily polluting process, and it was criticized by many people in the US, and US senators started to audition climatologists to say, I mean, hoping that the climatologists would say it's a bad idea to do this, right? And strangely enough, the climatologists did not say that, because they were convinced that you could do that because then there will be an energy transition in 50 years. I mean, something that really struck me is that the very same climatologists like Roger Revel and others who are explaining that there is a problem with climate change, they immediately kind of sabotage their work by saying that there's a problem with climate change, but we are able to do an energy transition before the climate catastrophe. That's something that we find very often in the papers around the year around 1980. The chronology, the forecast is as such. Climate change will be detectable. You will feel that climate change around the year 2000. It will have economic consequences by 2020, and it will be catastrophic by 2080. And when you write that in 1970 or 1980, 2080 seems to be science fiction. And it's obvious for everyone that there will be an energy transition in the meantime, in 50 years. So the oil company like Exxon is really putting forward this idea. Yes, of course, there will be a transition in 50 years. And finally, the climate catastrophe will come after the energy transition. Then there are the economists like William Nordhaus who love this idea of energy transition, explaining that it's better to postpone the effort because it will be easier to do the energy transition later when we will have all the technologies, especially nuclear technologies. And then there is the US government who also love this idea of transition. I found, I think, interesting archival materials about Robert Reinstein, who is the head of Group 3 of the IPCC when it was formed in 1988. And he was also the US negotiator at Rio, at the famous conference in 1992, the one that set up the UNFCCC. And he's in conversation with John Sununu. John Sununu is the chief of staff of George Bush, father. And John Sununu is very clear. Basically, at Rio, there is no money, so the US won't pay their damage because of climate change. There is no target, meaning that the US are not going to sign an international treaty limiting their own energy consumption out of no way. So play the technology card. Joue la carte technologique. Really, you have to put forward the capacity to innovate, to find technological solutions to this problem. And a few months after this conversation, there is a famous speech by George Bush saying that there is the greenhouse effect, but there is a White House effect. And the White House effect is going to counteract the greenhouse effect. So there is, I mean, it makes complete sense. If you're like, you know, representing the US, the first emitter of CO2, but also the first technological power, it makes sense to pretend that you're going to innovate your way out of the climate crisis. So play the technology card, and it is exactly what IPCC Group 3 has been doing since its first report. This is a graph I made out of the 6 reports. It's quite unreadable, I guess, but basically this is all about technology, and this is about change in demand, right? Most of the report is about high tech, like hydrogen, CCS, negative emissions, carbon capture and storage, carbon dioxide removal, non-existent technologies, right? I mean, there's so much ink spilled about technologies that are uncompetitive, very cumbersome, and that are not going to be developed in any case. So I'm going to stop here because I am also bossed around by. No problem. Yeah, no, but that's okay. Just to, I mean, I hope to have convinced you that this idea of energy transition is very strange. That this is not a serious notion. This is a slogan which came from very particular, very strange futurology, atomic scientists, neo-Malthusians. It has diffused in the 1970s for no good reasons. It has been transferred from the energy crisis to the climate crisis for no good reasons. I mean, just, sorry, I promise I stop here, but look again at this graph. Like the transition will take place somewhere in the 24th century. Now we have to do the transition not in 3 or 4 centuries, but in 3 or 4 decades. We have to do it at a global level. We have to do it despite the fact that coal technologies and fossil fuels are cheap, whereas this transition would take place in any case because coal, there will be no more coal, so of course you would go nuclear, right? So it's a completely different situation, and we have recycled this very strange futurology. Okay, thank you very much.